Hey folks, welcome to my channel Number Pen. So today we have an interesting problem in front of us. Let's take a few seconds to read through the problem. Suppose that the minute hand of a clock is 15 millimeters long and the hour hand is 12 millimeters. How far is the distance between the hour hand and the minute hand changing at 2 p.m., right? So we have a clock. Let's take a few minutes to visualize what the problem is actually stating. So let me draw the clock, and so this is a diagrammatic representation of the problem that we have at hand. I'm going to take the draw tool here to show what we want to, right? So I'm going to treat this as my hour hand, right, at 2 o'clock. So let me call this H, and I'm going to treat this as my minute hand. I'm going to call it M, right? So we've been given the lengths of H and M. So let's probably write them down. And I'm going to use the equation so that it's a lot more easier. So we have H equals the hour hand, which is 12. And then I have, again, I put my equation, which is my minute hand, which is M equals 15, right? And so we know that there is a triangle which gets formed between the hour hand, the minute hand, and the angles and the line which connects both the hands, right? So let's try and draw a representation of that separately so that we know, uh, right? I'm going to edit these points and let me try and yeah, so here we have. So this is your M and this is your H, right? And we have this distance which keeps changing. H and M are constant, but we have the distance, let's call it, say, X, which keeps changing, right? And at 2 p.m., we know that, if I can go back to the clock diagram, let me take this as my reference, right? This orange line is my reference. At 2 p.m., I know that this angle made by the minute needle is 90 degrees, and the angle made by the hour hand is 30 degrees, right? You know why is that? Because we complete, right? So this is 30, and so what is this angle? This angle is going to be, so I know that the angle that my minute needle makes with the reference line is 90 degrees, and what the hour angle makes is 30 degrees, right? So the angle between the two is what we have with us at 2 p.m., right? So what is this angle? And let me call this as theta, right? And let's write that down as well. I'm going to call it, where's my theta? Yeah, theta equals 60 degrees, right? And then, which means this angle here is my theta. That's my theta. So I'm going to write the equation to solve for x, right? I'm going to apply the cosine law of trigonometry, right? We have x square equals m square m square plus my, let me write this out first and then let's fill it up later. Minus 2mx cos of theta, right? And this is my h, and this is my square, and this is my mh, right? So we have this equation in front of us, and we know m, we know h, we know what is theta, right? So I'm going to substitute these values out here, and I'm going to replace m by the minute hand, which is 15, the hour hand, which is 12, and the minute into the hour hand, which is 2 into 15 into 12, into cos theta, which is my cos of 60, which is nothing but my half, right? So let's take a minute to work this out. What are we arriving at? In square is 225, right? 225 plus 144 is 12 square, minus cos 60 is 1 by 2. The 2 in the numerator and the 2 in the denominator gets cancelled, and we are left with 369 minus 189, which is 189, right? And what do we have? So your x is nothing but the square root of 189. Take a minute to calculate that. That works out to be 13.75 millimeters, right? So at the time 2 p.m., your x, which is the line between the hovered hand and the minute hand, is 13.75 millimeters. And while h and m are constants, we note that x is not a constant. So what is x dependent upon? X depends on the movement of m and h, right? So as m and h moves, you see that the angle made by the respective needles will change with respect to this reference line, right? So let us draw. Uh, so I'm going to use the cosine law and differentiate it on either side, right? 2 into x into dx by dt equals m square is a constant, so you have 0. H square is a constant, so you have 0. And then 2mh remains as 2mh. And then Cos theta becomes minus of sine theta, and you have this into e of theta divided by dt, right? So you have this nice equation here, which is going to tell you what is dx by dt. And what's the question we have in our hand? How fast is the distance between the hour hand and the minute hand changing at 2 p.m.? So all that we need to find out is dx by dt, right? So I'm going to rearrange this equation. Uh, you have two you have 2x dx by dt. I think we can just copy this quickly in the interest of time. And 0, 0, and 2mh into sine theta, sine of theta into d theta by dt. I'm going to keep this equation like this, and then we'll return back to this equation in a few minutes. So if I'm going to use this as my reference line, let me take a minute to show this as my reference line. What is my angle made by the H needle, which is the R needle? Let me call it, say, alpha, which is written here. And if the minute needle makes an angle beta with the reference line, right? So which means, let me, yeah, which means my theta is nothing but my beta minus alpha, right? And that's what we have written here, stating beta minus alpha, which means, and again, I'm going to differentiate it with respect to time on either side, makes it d beta by dt minus d alpha by dt equals e theta by dt. So we know that the hour hand moves 2 pi radians, right? Let's write this as 2 into pi radians in 24 in 12 hours, right? So it completes one full circulation in 12 hours, right? And we know that minute hand moves 2 into pi radians in 60 minutes, right? So in 1 hour, you see that the minute hand comes back to the same position, uh, you know, where it was 1 hour ago, right? So I'm going to rewrite what is d beta by dt, rewrite this equation, and call this, right? So what's my d beta by dt, right? So it's nothing but my minute hand rate of change of the angle, right? So it is 2 pi divided by 1 hour, which means as 2 pi minus, and what is d alpha by dt? It is the rate of change of the hour hand needle, right? So it is 2 pi radians divided by 12 hours, which is nothing but 2 pi divided by 12, which is my pi by 6, right? So this is gonna be this is gonna be equal to 2 pi minus pi by 6, which is my So we have this earlier equation out here. I'm going to just copy this again, the one which we last differentiated and left it at that stage. I'm going to copy this and paste this, right? I'm going to draw your attention back to the earlier working where we differentiated this particular formula on either side to arrive at what is the relationship between dx by dt, which is what we've been asked to find, and d theta by dt, which is what we arrived at. So d theta by dt, we have this number. And what is x? X is something that we calculated just now, right? So 2 into, I have my x, which is calculated to be 13.75 mm. So I put this out here as 13.75 into dx by dt equals 2 into m and h. We know it's 15 and 12 mm. Sine theta, theta at 2 p.m. is 60 degrees. So let me write this as 60. And into d theta by dt is nothing but my 11 pi by 6. So we eliminated all the unknowns. We are left with the solution for dx by dt. So let me take a minute to calculate this. E equals 2 into 15 is 30. I have sine 60 is sine 60 into 11 pi by 6. So 5.75 divided by 2 into 13.75, right? Yeah. So there we have the final answer. So 360 into 0.866, which is nothing but your sine 60 into 5.75 divided by 2 into 13.75, which is your 27.5 in the denominator. That gives us 65.19 millimeters per hour. Yeah, the final answer here, 64.19 millimeters per hour, is the rate of change of the distance between the H needle and the M needle at 2 p.m., right? So I hope you had a good understanding of um, the problem and the concepts discussed in this problem. Thank you for watching my video and happy to take feedback from my subscribers. If you do like my video, please do subscribe and pass me your feedback on this channel. Thank you very much and have a good day. Thank you.